It's a pleasure to introduce Margherita Disertori from University of Bonn. And the title of the book is Phase Transition of the Integrated Density of State of the Anderson Model arising from a supersymmetric hyperbolic sigma model. I just added sigma.
Can you hear me?
Yes.
Okay. Okay, please, I mean, in case you suddenly lose me and they don't react, and maybe I have my, write me an email if there is really a, okay, so thank you very much for the invitation. And sorry that I couldn't come in person. Okay, so this is joint work with Valentin Rapin, Constanza Rojas Molina, and Xiaoling Zheng. So here's the overview. I will start with some basic facts about the Anderson model and the corresponding integrated density of states. Then I will specialize to a particular kind of Anderson model arising in the context of H22 supersymmetric nonlinear sigma model, but this is also connected to jump processes with reinforcement. And for this special model, I will try to explain you what are the properties of some properties of the integrated density of states. Okay, so Anderson model. So this is a discrete random Schrödinger operator, and this is maybe the most famous model to describe electronic transport and wave propagation in disordered materials. You can define this model on any graph, but here I will just consider the case in ZD. So on ZD, this is an infinite symmetric real matrix, and it's made of two pieces. So the first piece is, wait, I will try to annotate, let's see if it works. It doesn't work any longer. Okay, I cannot annotate. It seems I could before. Wait, I'm sorry. Okay, so I will try again. Yes. Let me try again. No, okay, I cannot annotate any longer. Maybe. Yes, and now if I write. Okay, it seems that suddenly, yes. No, okay, it seems that I cannot annotate any longer. Well, okay, I will try to explain without annotating. Okay, so there are two pieces, H0. H0 is a deterministic matrix, and it's a diagonal in momentum space. And H1 is random, and it's diagonal in position space. So you have a competition between an operator which is diagonal in momentum space and an operator which is diagonal in position space. H0 typically is the lattice Laplacian. So a map from L2ZD into L2ZD. H1 is a diagonal matrix where lambda is some positive parameter. And on the diagonal, you have random variables Vj. And now I will assume, typically you assume that the variance of these variables is approximately 1. That the probability distribution is translation invariant. Normally you take the V independent or almost independent. And now what is the heuristics? Now if I take lambda equals 0, well, then I just have the Laplacian. So the spectrum is the interval 0 for D. I have absolutely continuous spectrum with delocalized or generalized eigenvectors. In the opposite case, when lambda is huge, then you can forget the Laplacian. H is approximately a diagonal matrix. And then since it's diagonal, the eigenvalues are just the random variables on this diagonal. So you have a pure point spectrum and perfectly localized eigenvector. And now the question is, if you take an intermediate lambda, which of these two effects wins? Okay, so here I'm collecting a few facts that are known. So the first question you can ask is, where is the spectrum? if your probability distribution is translation invariant, then you know at least by ergodicity that the spectrum is some deterministic interval, almost surely. Now, the second question is, what kind of spectrum do you have? For dimension d equal 1, it's known that you have, under certain conditions on V, it's known that you have pure point spectrum with exponentially decaying eigenfunctions for as soon as you have a little bit of disorder. If I take dimension larger or equal than 2, you can again prove pure point spectrum and exponential decay eigenfunctions. In two cases, either you take very large disorder, and in this case, you can be wherever you want in the spectrum, or you are at the edge of the spectrum, and at the edge of the spectrum, there are less eigenvalues, and then for any values of lambda, you can prove localization. There is only one example for the two Anderson models that I know where you can prove really a phase transition between absolutely continuous spectrum and localization, and that's not on ZD, it's on the Bethe lattice. And there you can really prove that if the disorder is very large, you have localization, and if the disorder is small enough, in the center of the spectrum, you have the AC spectrum with delocalized eigenvectors. So in dimension d larger or equal than 3 on the lattice, it is still a big open problem to prove delocalization in the bulk of the spectrum for a small lambda. Okay, so now what are the observables we can look at to get information on the spectrum? The easiest observable you can look at is the integrated density of state. So how do we define it? First I take some finite volume. I restrict my operator to this finite volume with some boundary conditions. Now I have a real symmetric matrix, finite matrix. So I know it's diagonalizable with real eigenvalues. So what we can do, we can count the number of eigenvalues smaller than a certain energy, and then divide by the total number of eigenvalues. So that's the finite volume integrated density of states. If I send now the volume to infinity, what we obtain, so you can show that the limit exists, and what you obtain is the integrated density of states. So it's a kind of limit of the fraction of eigenvalues smaller than a certain energy. Okay, so in the standard Anderson model, the V, the potential V on the diagonal is given by IID random variables. Okay, now I am assuming that the probability distribution of a single random variable is absolutely continuous with respect to Lebesgue. So I have some density mu times dV. And to simplify, to make it clear, I assume also that this V is between 0 and infinity, and some regularity conditions. So then the spectrum of H is containing 0 infinity, almost surely. And actually, near 0, there is almost no spectrum at the bottom of near E equals 0. And the fact that there is almost no spectrum, this phenomenon is called the Lifshitz states. And so what does it mean? If I take E very small, but still positive, then the fraction of eigenvalues below E is exponentially smaller in the energy. So you have E minus a constant times 1 over the energy to the power D over 2. And the constant C1 and C2 depend on the details of the probability distribution for V. Now, to understand how small this is, you should compare with the case when there is no randomness. So you only have the Laplacian. In that case, the integrated density of states is, when you compute, is just energy to the power D over 2, which is much, much bigger than this exponential. So somehow this random potential is pushing the spectrum away from the boundary. And now, what is the approximate mechanism of these? I'm assuming that V is positive. So if I have H0 plus lambda V, this is larger than H0. If I want to get near to the bottom of the spectrum, I'm trying to make V as small as possible. And the idea is that I have independent random variables, and I want many of them to be small. So the probability that many independent random variables are small is very tiny. And that's actually the mechanism behind it. Okay, now, fine. So what now do I learn from these integrated density of states? So do I know something on the spectral type? And actually the answer is yes and no. If you are on the edge and you can prove there are Lifshitz states, so this is the case for IID random potential, well then using the fact that you have so few eigenvalues, you can indeed prove that you have pure point spectrum and localization. On the other hand, if you are in the bulk of the spectrum, far away from the boundary, well then the integrated density of states cannot see a phase transition. And well, there are several results on these, but said in a more or less, the argument goes as follows. So if you know that the probability, the density for one random variable has a certain regularity in the energy, then the density of states as a function of the energy has more or less the same regularity. Maybe you lose a little bit. So a phase, when you have a phase transition, it means that you would expect that the behavior of, as a function of the energy of your integrated density of states changes drastically if you change the parameter lambda. But this result tells you that the behavior of the integrated density of states is more or less the same for any choice of lambda. So you cannot see a phase transition from here. Okay. So this is the situation for IID random variables. Now, we'll move to our example of Anderson model. So, and the point is that here you don't have IID random variables. So again, on ZD, I have the same structure. My random operator is a sum of two terms. The first term is deterministic. And well, so it is not really the Laplacian, the discrete Laplacian is the shifty discrete Laplacian, where you only take the off-diagonal terms. So H0 is minus P, and P is the adjacency matrix for the lattice. And H1 is again a diagonal matrix, so a multiplication operator. I have a parameter in front 1 over W, which is like the lambda before. And the V, so for technical reasons, you write V as twice the random variable, but anyway, this is the random potential. And now this family of random variables has a certain probability distribution. What is the difference is that now the parameter W, so lambda, is not just in front of V, it's actually also in the probability distribution. That's not as in the standard case. So we know, so what do we know about this probability distribution? Well, we can write explicitly the finite volume marginal. So you take some finite volume. Now the marginal in this finite volume is given by the blue formula. So there is a prefactor, which is a constant. In the exponent, we have a scalar product 1H1. So where this is just the brackets are just the scalar product in the sum over J of, so F scalar G is a sum over J of Fj times Gj. So the first term 1H1 is actually modulo constant, is a linear combination of beta. So that's not a problem. But now you have a second term, eta, H inverse eta. And there, suddenly, you see that, the beta don't appear linearly, so I'm introducing interaction between the betas. And now then, if I look in front, I have 1 over the determinant. Again, I'm mixing up the variables. And then an important condition, I take only configuration where H is strictly positive, which again is imposing it is imposing an interaction between the betas. Actually, even if this looks very horrible, you can compute explicitly the finite volume Laplace transform, and that's the very last formula. So if I take a vector f, the average of exponential f star beta is given by a product over all points j of a function of fj. And then I have a product over nearest neighbor terms, exponential minus wij, a function of fi, and a function of fj. So what you see from this formula is that if I look at beta at 2 points that are not nearest neighbors, then this formula becomes a product. So even if in the first blue formula, it seems that these random variables are horribly interacting, it turns out that they are really independent at distance 2. Okay, so now, what are the properties? So the first property, the random variables are independent at distance 2. The way this is, so maybe this I didn't say. So the eta is a vector which is counting at each point j the number of points in the lattice nearest neighbor to j, but which are not in the volume. So these are the so-called wire boundary conditions.
Is there any physics behind this form of randomness?
I have to, yes, but not in the way you would expect. I will show in a minute where it comes from. So I don't know if there is any model, so physical model, which is described exactly by this random potential. So this operator appears naturally looking at another model, which I have to show you. So you have to be a moment, just be patient for a moment. Okay, so maybe actually, whatever vector eta I choose, this will still be a probability measure. But the special choice of eta we are taking guarantees that we can define an infinite volume probability measure. Okay, now the random operator is ergodic, and you can show that the spectrum is exactly the interval 0 infinity, almost surely. And now comes the important factor. So if I don't take the random potential at all, so I put beta equals 0, then my unperturbed operator is actually the shifted Laplacian, so it's the spectrum is between minus 2D and 2D. So it's centered around 0. But now the condition now, whenever we put some randomness, the matrix H beta has to be strictly positive. So this is saying that actually the edge of our random operator, the edge of the spectrum for the random operator is in the middle of the unperturbed spectrum and not at the edge of the unperturbed spectrum. So the fact that so if you look at beta equals 0, your operator is not strictly positive. So the condition A strictly positive is saying that if one potential is small, some other potential must be very large. And so you cannot have that many V are near 0. And so that's what is, so you are destroying the standard mechanism to create Lipschitz states. Okay, and now still one last thing, and then I will come to where it comes from. So as in the case of standard Anderson model, I would like to see a little bit what I should expect. So since now W enters in the probability distribution, I have to compute a bit explicitly what is the average and what is the variance of my random potential. So by exact computation, the average of 2 beta j over W is 2D plus 1 over W, and the variance is given by 2D over W plus 1 over W squared. Okay, so if W is huge, you see that your operator is approximately 2D minus P. So you're reconstructing the discrete, the lattice Laplacian. And the variance is extremely small. On the opposite, if W is very, very small, well, your potential is fluctuating like crazy. So basically, you can forget the discrete part, and your H is approximately a diagonal matrix. So W large is the analog of weak disorder, and W small is the analog of strong disorder. Okay, now I have to explain where it comes from, indeed. So it is a bit, the origin is a bit strange. So in the process of studying the true Anderson model, so it's very hard to prove a phase transition for the true Anderson model. So people started looking at other matrix models with the same phenomenology. And one of the most famous one is the so-called band matrix model, which is actually also physically relevant because you could think of metallic grains. So inside each grain, you have all energy levels are completely disordered. So you have a small GUE matrix, but then they are connected in a kind of lattice, in a kind of lattice, so that the random connection between these grains go only up to a certain distance. So what you obtain is a matrix which is random, but you have more or less independent random variables in a certain band centered on the diagonal and approximately 0 variables outside. And you expect that also this type of model exhibits a phase transition. So the hope was that there you have more average, and so you can prove more results. So anyway, whatever the model is, you try to get information on the spectrum. You want to study the Green's function for this random operator in absolute value square. And you can, using the supersymmetric approach, you can reformulate this as a new model, which looks like a statistical mechanical model with spins that are strange. And these spins, they actually, instead of like in the Ising model, you have spins which is plus or minus 1, or spins on the sphere, you have spins leading on a certain, the spin is a small matrix with real and Grassmann variables. Okay, so you can do non-rigorous computations, and actually you can show that there is indeed a phase transition, but everything is non-rigorous. So trying to figure out a way to devise a model where you can do rigorous computations, but which is still describing the physics, Dirnbauer came up with this toy model where your small matrix is replaced by a small vector. And it turns out that here you can indeed prove a phase transition. Okay, so how is this model defined? So you think about you have a finite volume and you want to define a spin configuration on this volume. So the spin is a vector at each point, is a vector with 5 components. X, Y, and Z, these 3 are real. Psi and eta, these are Grassmann variables. If you know Grassmann variables, okay, then you will not be surprised. If you don't know them, don't worry. So these are, you can make all these rigorous. So basically, these are objects that anti-commute and the corresponding square is 0. So you can think of X, Y, and Z as real numbers. Or, if I want to be more precise, these are even elements in a real Grassmann algebra, which have a first component, which is a real number, plus additional terms that contain Grassmann variables. So you can forget this. Now I want to define a kind of scalar product on this space. And the scalar product is defined as, so I take S scalar S prime, this is XX prime plus YY prime minus ZZ prime plus something with the Grassmann variables. So if you forget the Grassmann variables, what you have here is not a Euclidean scalar product, it is a Minkowski inner product. So it's not positive definite. So now, in the case of a standard ON model, your spin is a vector in Rd, Rn, and you are imposing a nonlinear constraint. The norm of your vector has to be 1. We do the same here. We impose a nonlinear constraint, but now the norm, sort of norm of the vector is -1. And if you insert this in this definition, you discover that then Z, the third component, must be a function of the other 4. So actually, I should have written plus minus Z is plus minus the square root, but you can always choose the positive side. So what happens if you forget the Grassmann variables is that your spin lives on a hyperbola, on the space H2. And since you have Grassmann variables, you are decorating this space with 2 additional Grassmann variables. If I am in a standard ON model in statistical mechanics, you may or may not add a magnetic field which is favoring one direction. In this model, you don't have really the choice. You must add a magnetic field because this spin lives on a non-compact space. So if I don't add a special direction which is breaking this non-compact, which is choosing one particular non-compact direction, you are dead. So we add this magnetic field, and now, as in the case of a standard ON model, I define a Gibbs measure. So the Gibbs measure, I take the product over all I and j nearest neighbors, and they have exponential weight, the scalar product as I as j, and then we have for each point, we can add a magnetic field eta j, and so we have Sj scalar a particular direction. And finally, we have a delta enforcing the nonlinear constraint. Here, the W is really the same W that appeared in the random Schrödinger operator, but here it plays the role of an inverse temperature. Now, it's not obvious, but actually this measure is well defined, and it's really favoring the spins to be in this, aligned and all in the direction of E. So this representation is great to have an idea about symmetries of the model and what you should expect, but it's hard to do computations with that. So once again, Martin Zimbauer had the idea of changing coordinates. So he went to some coordinates that are pretty natural for when you live on the space H2, and these are the so-called horospherical coordinates. So you map the independent variables x, y, xi, and eta into in a new set of variables, us, psi, psi bar. And now the measure in these new variables takes the following form. That's the first equation. So I have exponential of, so I take a sum of their nearest neighbors, and now I have an hyperbolic cosh of ui minus uj minus 1. So you see that this is just if the gradient is almost 0, then this is approximately ui minus uj squared. So it's just a generalization of a Gaussian. Then the second term is eta j times hyperbolic cosh uj minus 1. But once again, if u is almost 0, this is uj squared. And finally, the S and psi variables, they appear as Gaussian expressions with a matrix M that is written below, and this matrix M depends on the U configuration. Okay, now, if I'm interested only in observables that depend on U but not on S and psi, then I can integrate out S and psi exactly, and I obtain the U marginal, which is almost the same, but now the S and psi matrix, they generate determinants. The Grassmann integration generates determinant of M, and the S is a real variable. When we integrate, we obtain 1 over square root of the determinant. So putting the two together, we obtain square root of the determinant. And now I can insert the exponential minus U, which is in the measure, inside this determinant. So putting all this together, exponential minus U, M exponential minus U, looks exactly like the random Schrödinger operator I described to you. So it is minus the adjacency matrix plus 1 over W, and then there is this diagonal random variable, which can be written explicitly as a function of U. So now the connection between this nonlinear sigma model and the random Schrödinger operator is the following. If I take my random Schrödinger operator and I'm studying some function of the random potential, f of beta, if I take the average, well, this is the same as taking the average in this U marginal measure, replacing beta with beta of U. And I can even go backwards to my measure with spin S. So this is the same as taking the integral of a d mu S with real and Grassmann variables. And now I replace U with the log of x plus z. And actually the point is now you can go jump back and forth between these three representations. Okay. So I claim that this model is also related to stochastic processes with reinforcement. And the connection is the following. So, so the connection is to the so-called vertex reinforced jump process, which was initially suggested by Werner and then studied by many people. I cannot do a full list. Okay, so this is a continuous time process. In this case, I'm taking this on ZD. And the process goes as follows. So assume at time t, you are at position I, and you know the history up to time t. Then you jump to a neighboring point j with a rate which is w times 1 plus lj of t, where lj of t is the total time you spent at the target point up to time. So if you already spent a long time in some point, then you are jumping back to this point very quickly. So this is a process which is reinforced towards the past. Okay, and now what is the connection between this process and our nonlinear sigma model? So it was proved by Christophe Sabot, Pierre Tarès, and then also Xiaolin Zheng that the vertex reinforced jump process in a finite volume is a mixture of Markov jump processes. So now I'm not going to write this rigorously. You should first do some time changes, go to some discrete time, but in any case, more or less, that means that the probability of some event in your VRJP in a finite volume can be written as the analog probability for a Markov jump process with a fixed jump rate W. But now these jump rates are random, and the randomness is parameterized by U, where U is the random variable we defined before. And the U marginal I wrote before is exactly the mixing measure for VRJP. Okay, so now I introduced three related models. The nonlinear sigma model, which was introduced as a toy model for quantum diffusion. VRJP, this is a stochastic process with reinforcement, And H beta, it is a random Schrödinger operator, which is a pretty unconventional probability distribution. So what do we know about these models? So for H22 and VRJP, we do know that there is a phase transition in dimension 3 or larger. And what does it mean? So for H22, you know that there is a disordered phase when W is small, which means strong reinforcement. And there is a quasi-ordered phase when W is very large. And this goes back to a paper with me and Tom Spencer and Tom Spencer and Martin Zierbauer in 2010. In the same way, the stochastic process has a transition. So it's recurrent if W is very small, so strong reinforcement, and it's transient if W is very large, weak reinforcement. And this was proved a bit later by Christophe Sabot and Pierre Tarès. So now the natural conjecture is, well, can we use this information to get to prove something about this random operator in dimension 3 or larger? Can we prove that there is also there a phase transition? And interesting enough, here we are more or less in the same situation as with standard random Schrödinger operators, which means if W is very small, so for strong disorder, you can prove localization. And using the standard tool, so fractional moment method, you just use the same tools you use for standard random Schrödinger. And this was proved by Collevecchio and Zen in 2021. On the other hand, you would expect that if W is large, in the bulk of the spectrum, there is some AC spectrum. But for the moment, we don't know how to prove this. Okay. Now, now I would like to explain is this interesting fact that it seems that the integrated density of states, contrary to the case for IID random variables, it sees the integrated density of states sees something of this transition, or the transition we would like to see. And so this is a result with Valentin Rapin, Constanza Rojas Molina, and Xiaolin Zheng. So what we showed is that if you are near the edge of the spectrum, so it's actually really for a small energy, and we are in dimension larger or equal than 3, we do see a change in the behavior of the integrated density of states, and precisely for strong reinforcement, the integrated density of states behaves like square root of E near the boundary. And for a weak disorder, it behaves, so it's smaller than the energy. So it could be even much smaller, but it's certainly smaller than E. Moreover, we show that there are no Lichy states in this model. So in dimension 1, we can show this for any choice of the disorder. And in dimension 2 or larger, we need to be a strong disorder. Again, more precisely, because this is a bit vague, so what we proved is an upper and lower bound on the integrated density of states. We have a general upper bound which says that the integrated density of states is bounded by square root of the energy times square root of W. And this is very general. It works for any energy and for any W. On the contrary, if we are in the region of localization and we have an energy which is small enough, then we have a lower bound on the integrated density of states, which is again square root of E with a log correction. And in dimension 1, we can do this actually for any choice of W. Actually, for a W can go to infinity. Now, to prove that there is a change in behavior in dimension 3 or larger, we can show that the upper bound is actually better than square root of E, and actually we obtain an upper bound which is proportional to E. And again, this works for any value of the energy, and but the constraint now is that the W has to be large enough. So you have to be in the regime of weak disorder. Okay, so I can maybe give us, so since I have still 20 minutes or less, or
bit less.
15 minutes, or I mean,
Yes, 15 minutes.
I mean, I don't want to abuse. Okay, so a little bit. So the idea of how you prove what is the strategy. So you have two different ways of proving this. So you need a strategy to prove the lower bound and a strategy to prove the upper bound. So for the lower bound, there is a standard bound that is not for our operator, it's generally for random Schrödinger operator, saying that the integrated density of states is bounded below by 1 over the volume. So the integrated density of states is defined in infinite volume, but now we take some finite volume. We take the matrix restricted to this volume with Dirichlet boundary conditions. We invert it and compute the 0, 0 element. And now the lower bound is the probability that this matrix element is larger than 1 over the energy, and you have to divide by 1 over the volume. Okay, so we could say, well, okay, so we have an explicit probability distribution. Or maybe we can say something about this matrix element. Now, actually, the answer is no, we have a problem, because we have very good information on H inverse 0, 0 with no boundary conditions, but we know we have no direct information. The moment we add these Dirichlet boundary conditions, we are slightly modifying the matrix, just adding a small diagonal piece, and that's enough to sort of break the structure in our probability measure. So what we do is we try to reduce the problem back to the case. We have to get rid of these Dirichlet boundary conditions. So to get rid of them, you start remarking that, noticing that using random walk representation, your Green's function with Dirichlet boundary conditions is always positive and bounded above by the Green's function without Dirichlet boundary condition. So I can always bound the Dirichlet Green's function below by H inverse. And then I have a sum over correction terms that are Green's function going from 0 to the boundary. Okay. That's why we can now do this game only in the regime, in the region where we have localization. So in the regime where we have localization, for W very small, we know that with very large probability, the Green's function H inverse decays exponentially. So we can show that then the correction term is very small. So since the correction term is very small, then we can, instead of studying the probability for the H with Dirichlet boundary condition, we can study the probability that H inverse with simple boundary conditions is larger than something. Okay, so now can we say something about this last probability? So now here you have to really use the symmetry properties and the special form of your probability distribution. So it turns out that you have an explicit formula for the probability distribution of this matrix element, as long as you condition on the random variables that are not in 0. And the explicit formula is what I wrote in blue. So we have 1 over square root of y times exponential minus a minus y squared divided by 2y. This is a constant. And the parameter a contains, depends on the random potential not in 0, in everywhere else. It's some explicit formula. Okay, but then you can use this information to, so you bound the probability using this explicit formula for the probability distribution, and you extract quickly the square root of epsilon. So this is for the lower bound. So let me quickly say what, how do we bound the upper, how do we do the upper bound? There you use a strategy which is pretty standard in random Schrödinger operators. So you bound the integrated density of states in finite volume with a sum over all the points in your volume of the Levy concentration of the conditional measure in that point computed at twice the energy. And now, once again, since you know explicitly the conditional probability distribution of one random variable, then you can do bounds. So for a very stupid bound, if I go back to the probability distribution I wrote, a stupid bound is to bound the exponential by 1. And then I just have 1 over square root of y. So if I integrate between 0 and e, I get something proportional to square root of the energy. So that's how we get the bound, the upper bound. In dimension larger or equal than true, this upper bound is bad. So we have to study more precisely what is this density. And we bound this density by 1 over a, 1 over square root of a. So we have to use a little bit more details. And the point is that these random objects, 1 over a, can be bounded by a constant, using again informations on your probability. So you get a bound which is now proportional to the energy. Okay, so I think I have already killed you, so I will now just go over some open problems. So, so what we have a partial picture. So, for example, we have for very strong disorder, we have this behavior, square root of e near the boundary. And we prove there is, in that case, also no Lifshitz tail. We expect there is no Lifshitz tail also for weak disorder. But there, so if I go back to my result, what is this? Right. So in the case of W large, n of e is bounded above by e. But you would expect that this is the correct behavior. So we would need a lower bound, and we still don't have it. And also, all these results we always need either W very small or W very large, and you would like to see what happens for any value of W. So there is still something missing to complete this picture. And now, of course, the next question is, fine, you see some kind of phase transition in the integrated density of states. Can you now prove that there is really AC spectrum in the bulk and pure point spectrum? And still, that's still a wide open problem. So we are still far away from. Maybe the interesting question is why are we don't see the Lifshitz tails? And actually, it seems that actually you may think, well, we have this very special probability distribution. But actually, it may be that the only really important effect is the fact that you are putting the constraint H beta is positive. So you could ask the following question: take H is minus P plus lambda V, but now V is some IIV random potential, which, well, here I wrote bounded, but you could take the probability distribution you like best. And now you add the constraint H is positive. Is this constraint enough? So you are creating interaction, but just through this constraint. So the question is, are you losing the Lifshitz tails or not? Okay, and I think I think it's enough. So I will stop here. Thank you. So I need to see the people.
So questions?
So in your last question, I guess the opposite to that question is, okay, so if you try to remove the h beta greater than 0, you can't do the integral for the beta, right?
You mean if I try to remove in the definition of my, you mean in this particular model?
Yeah, you need to have, you can't, obviously you need to have this to...
Yeah, I mean, then you suddenly are dividing by a determinant, which is no longer well defined. I mean, it could be 0. I mean, if you remove h beta strictly larger than 0, then suddenly your function is not even well defined.
So, but there's no way to. So you're saying that if you remove the beta, then you get a spectrum which is symmetric around 0.
Exactly.
But can't you just sort of shift everything in the definition of the beta? Like it was the fact that you started off from the adjacency matrix rather than the Laplacian.
You mean look at the operator? Yes, but this will not. Yes. Yes, but then
Alternatively, like if you...
I mean, you're just shifting your problem completely, but or are you proposing to take really the same beta, but now taking minus Laplacian?
Okay, well, I mean,
this you could try. So either you shift your full operator and then you're doing nothing because you're just shifting the whole spectrum, or you're really modifying your matrix. And then, for example, you could say it's actually minus Laplacian plus beta. And then you require, then saying that H beta is strictly positive is putting much less constraint. I agree, because then the boundary would be just, the boundary of the spectrum is perturbed or unperturbed operator would be the same.
I guess, I mean, so
But then,
if you took the, I guess, W to infinity E,
yes.
Eta, then you get the variance of beta going to 0.
Yes, yes.
Then you don't recover the... You recover, is the mean 0 of beta?
So you would like to see what is the limit here for beta? So what you mean in this probability measure? So this probability,
As in, I guess, so in the standard model, if you remove the randomness, you're still left with the diagonal of the Laplacian. The other way to think about that,
yes.
You take the variance of that randomness to 0, then you recover the Laplacian. If you take the variance of beta to 0, do you recover the adjacency matrix or do you recover Laplacian? I think.
I mean, it depends. If you're just forgetting this probability distribution, you're doing this just for one. So where was I? Here. No. There is. Here. So if you just look at the sort of the average of the matrix, then you just have the average of the 2 beta. Then when W goes to infinity, you really converge to minus the Laplacian.
Okay.
That's a nice.
So that seems to me it's not so different then from the. It seems like it's closer to the original case than what maybe.
So the point is that your beta typically are positive, are large enough to guarantee that your matrix is positive. Mm-hmm. And the average of beta typically, so when W is very, very large, beta is concentrated near 2D. Beta is very, very concentrated near 2D. But now in the probability measure, it's a bit difficult to, I mean, you have to be a bit careful. Yeah. You have all the variables and you have to be, the W is everywhere inside. And I agree, it should be actually, I also agree that actually it should be easier when W is large, it should be easier and easier to study properties. For example, I cannot believe that we have Lipschitz tail for W very, very large because we are convergent to the Laplacian. still, to prove there are no Lipschitz tail for W very large, you should prove a lower bound for the integrated density of state, and we still don't have it. Which seems strange, I agree. Maybe we are missing something very stupid.
And the other thing was with that, in your first theorem there, the phase transition in D greater than 3, what is it that you would expect for the Anderson model again?
Sorry, I didn't hear the
The
question.
original Anderson model, what do you expect
Yes.
the analog of statement 1? Or the first thing you've written in the blue?
One, so you mean that there is a phase transition? Well, wait. For a standard Anderson model, you actually, with IID random potential, you have no phase transitioning. You always have exponentially, you have Lipschitz tails.
Question?
Yeah, a rather basic physics question. So in the beginning, you had to impose a magnetic field in Z. You had this E00100. So can you get away with just...
Sorry, I'm trying to find the...
But can you get away with just putting the magnetic field on the edge of the volume? Like, is it just it's just a, yeah, I don't know if the question makes sense.
Yeah, so you mean not putting the magnetic field on just one point?
But just on the boundary of the volume. So
yes, absolutely, yes.
So
you don't need to put the magnetic field everywhere.
Yeah.
Actually, it's enough to put it, actually, in the toy, if you go from the probability measure with wired boundary conditions to this model, that means that you're actually putting your magnetic field just on the boundary of your volume. But you can actually, it's enough even to put only on one point.
Yeah.
Because it's just to make your measure well defined.
Thanks.
Other questions?
Yes. Rather early in your talk, you mentioned an argument saying that, I'm not sure I understood correctly actually, so that by looking at the density of state, you should be able to detect the transition. Like the thing you said suggested that there should be a singularity in the density of state. Did I misunderstood what you said there?
Well, it's not really. This is a hope. So, so for a certain time, it was people were wondering that maybe you can detect the phase transition between AC spectrum and the pure-point spectrum already at the level of the integrated density of state. Now, but now it was proved that if you have IID random variables, this will never happen. It's impossible. So my argument was the opposite, was to say that if you have IID random variables, you will never see the phase transition at the level of the integrated density of states.
Right. Okay. So there could be a transition, but you won't see. Yes. Okay. You won't detect it that way. That's what you are saying.
Exactly. Exactly. And then the hope is that the point is that this is for IID random variables. And now, since in the model we are looking at the variables are not independent, then you may hope that that maybe, and it seems that it's seeing something. I don't know if actually you can prove really that you have AC spectrum from the integrated density of states. Maybe not. But you may hope that since the integrated density of state is already, it seems already to see something, maybe it will be easier to prove the phase transition. But I have really no idea. It's just a hope. It's just that it's interesting that the fact that you are, it's not, what is not clear is that, so what is the mechanism? So is the reason why you see a different, something different at the level of the density of states due to the fact that, so the first thing you could think is, well, we don't have IID random variables. So you don't have IID random variables. So the argument that the integrated density of states cannot see the phase transition doesn't work. But now, what is the dependence that you're really using? Is it because you see, if you look at the random variables, they don't have so much a dependence. They are correlated only at distance 2. So could it be that it's this, or so it's a special form of our probability distribution, or is this constraint that you are forcing the random matrix to have the the lower bound of the spectrum far from the lower bound of the unperturbed, so the random matrix without randomness. Could it be that it's just this fact? And it's a question. I really have no idea. So there is a lot to look at, to research here.
Okay, so I think it's time for lunch. Thanks a lot, Margherita.